Well, thanks everyone for being here today. So as Mary was saying, I'm Victor Prost. I'm the deputy head of the Magnet Vacuum and Cryogenics Group at Renaissance Fusion. And so Renaissance Fusion is a startup based in south of France that aims to deliver low-cost fusion energy to the grid. So as I think with try that again. Perfect. So we all know there's an increased demand for energy production. We'll almost double by 2050, and on top of that, we want to have clean energy delivered to our systems. And so fusion energy tries to address those two main challenges. And so thanks to all the speakers before that described fusion energy, tokamaks, and all that, I'll just skip through the next slide. So there's currently a race to fusion. When I say currently, it started in the 60s, but it's been very intensifying in the past 10 years. And so here we have a plot of the performance metric of how close those fusion machines are to providing net electricity, and you have here the years. I'll focus on one type of machine called magnetic confinement machines. They are used to, they use intense magnetic fields to confine the plasma in which fusion reaction will take place. In magnetic confinement machine, there's mostly two types, tokamaks with heater that we've seen, and stellarators. Those two representing in red dots, and that the closest to breaking the barrier of net energy production. Renaissance Fusion is betting on stellarators. And why are we betting on stellarators? So tokamaks outside of ITER are easy to build. There's hundreds of tokamaks existing on research facilities nowadays because they're axisymmetric devices. We have repeating D-shaped coils that provide the magnetic field. The downside is that they are difficult to operate. There's a central coil that provides a pulsating field that drives the current through the plasma, and that current is useful and necessary to provide a twist in the plasma to confine and have fusion happen. But that pulsating, very intense current in the orders of mega amps makes the device difficult to operate. It's subject to instabilities that can destroy the machine itself. On top of that, the fact that it's pulsating means it's not always on. There's time for recharging the central solenoid coil, so we're not producing electricity all the time. Stellarators, on the other hand, they provide this twist in magnetic field using 3D complex coils. And so which makes them difficult to build, but there's no pulsation, they're steady state, there's no intense current, so they're simple to operate. As long as we turn it on, then they will be functioning and deliver power essentially forever. Stellarators are not a new thing. They've been researched, from also the start of tokamaks, 60 years, but there haven't been a lot of research into building them, only a few in the world. And what Renaissance Fusion is trying to do is to have two things, both a simple to operate machine, but also a simple machine to build. So bringing essentially the ease of construction of tokamaks to the stellarator machine. And we try to do that through three main pillars. One, we've mentioned magnetic confinement. There's a new type of superconductors. I say new, it's been here from the 1980s, but it's been now essentially reaching a high TRL that it can be used in fusion machine. Those are called high temperature superconductors, and they enable to provide more intense magnetic fields than regular superconductors. That allows to decrease the size of the machine. So boiling down to what you saw with ITER, we could have the same power of 1 gigawatt electric machine in a machine that's only 4 times the size of ITER and 10 times the volume of plasma. And so those are the benefits from high temperature superconductors. At Renaissance Fusion, we're building our own R&D manufacturing line of superconductors. It comes traditionally in format of 12 millimeter tapes, but we're developing a new technology to have wider sheets, so 1 meter wide sheets of superconductors. And you'll see how this is relevant to the next steps. The second part is if we go to more compact machine with the same amount of power, it means that we have more power density. It means that if we have a solid wall, the wall will increase increasingly high heat loads that it might not bear or withstand through the lifetime of the reactor. And so what we're using here is similar to molten salts in fission reactors, a liquid first wall. And so that liquid first wall has two main benefits. First, it's going to be our heat transfer fluid, so it will allow us to cool the reactor core and extract the heat from the core. But also, because of its properties, it's here thick lithium liquid walls, we can block all the neutron radiation and also provide the tritium that we need to fuel the reaction. The third one is that we're trying to simplify how stellarators are made. Instead of going through 3D shaped coils, we're going for simple cylindrical structures on which we're going to laser engrave circuit patterns. So similar to printed circuits. And that's why we need wide superconducting sheets. That allows us to do printed circuits on superconducting materials. And then we're going to wound those printed circuits over a former, a simple cylindrical former, and assemble that to produce the complex magnetic field. And so you see, okay, although those are great ideas, they're very, risk-prone ideas. And as Angel was saying, the startups are taking risk, and all the job from Renaissance Fusion is to try and do experimental proof to de-risk all that project, to show that all those technological pillars are actually feasible and have the performance and meet the objectives that we want. So in order to do that, we have a roadmap in 3 steps. So the company was created in 2021 as an independent initiative, although one of the co-founders was a professor at a university in New York. And so it started in 2020 with 2 people. And now towards the end of 2024, we're around 60 people. And that first phase that we're just about completing is about demonstrating those 3 pillar technologies. And so we've built devices both for HGS manufacturing, demonstrating free surface liquid metal flows, but also demonstrating that the tools that we use to simplify the reactor allows us to provide complex magnetic field using this laser engraved printed circuit technology. So we did that thanks to private funding, a seed funding round of around 16 million euros, but also public grants from the French government. And that was crucial in sustaining the growth of the company because between 2 private funding rounds, we had essentially the public grant to allow us to bridge the gap. And so now we're closing the Series A's that will allow us to move from those building block technologies, putting them together into an experimental fusion reactor. And so that fusion reactor will be proving net energy and not net electricity, but that will be already a major milestone because essentially what we're trying to do here at a small scale is to do the same thing as ITER, but using those novel technologies. And to maybe put that in context, we're using 2024 essentially technologies, while ITER was designed using 1990s technologies. Then we're going to use that first reactor as a stepping stone to a larger device that will produce net electricity. And so schematics are all nice, but what, aside from you trusting me, what do you actually, see? And that is what we have to show to investors, not just thematic and ideas, but actual deliverables. So in terms of HGS manufacturing technique, we've been building our pilot HGS manufacturing line. And so you can see huge vacuum vessels. Some of them were subcontracted, as Benjamin was saying, in Spain, because there's already a fusion industry in Spain. And so right now we've designed, modeled, and have manufactured most of the parts for the R&D production line of HGS, and we're entering the phase of commissioning and doing the first deposition to create our own HGS tape. Then free surface liquid walls. So we've been building pumps and system that right now is a demonstration of a section, or a cylindrical section of a reactor, in which essentially we have the pump here pushing liquid metal through the top, and then instead of falling straight down in the middle of the chamber, we're coating the entire cylindrical surface with liquid metal. If you're interested, I'll share a link to our website as well as the YouTube channel where you have actual videos of that happening. And then lastly, as you can see here, those are essentially laser engraved copper sheets, because as we are a startup, we want to move everything in parallel. So if we don't have yet the HGS white sheets, but we're doing tests on copper sheets to show that we can laser engrave copper sheet that will reproduce target magnetic fields that are relevant to stellarators. So again, just to stress how important all those experimental demonstrators are, is that those demonstrators allowed us to build trust with the investors. Publishing, although it's not the main, I would say, things in private ventures, but for us, doing scientific publication, patent filing, delivering on even smallest milestone that de-risked the project was crucial to essentially sustain growth, sustain funding, and then get more investors on board. And so that allows us to double the team size almost every 8 months, and now we're around 62 people. So just to stress a bit more, instead of just delivering project and building devices, we want to essentially develop our own technology and own our unique manufacturing tools, which that means that on top of what I showed, the deliverable, the projects, instead of just saying, okay, I'll ask the company to build this for me, we'll then acquire and build the tools so that we can then make those things on our own. So for example, we've co-designed and manufactured a roll-to-roll laser engraving machine, which was a first in kind that allows us to do that printed circuits not only on copper conductors, but also on white HGS tape. We've been building tools to wind and make our own HGS coils, do some corrosion testing at high temperatures for the liquid metal flow. As you can see here, you can see the liquid metal flow flowing inside the chamber. And so developing the pump and all this. And this is crucial for us because fusion is a long-term plan. It's not going to happen tomorrow. It's going to happen in a couple of years. But as a startup, we need revenues, and living off private funding. It's nice if we have a fusion for energy backing us, but if not, we need to have products and clients and customers to have revenues. And so all of those technologies that we essentially push for owning and having in-house is to also have products and solutions that we can then sell to research centers, other fusion companies, but also other applications. So all of the technologies that I've shown you are technologies that can be used in other fusion startups and also other research institutes. So it's hard to make those products. And luckily, being in Europe means that we can collaborate with research centers in Italy, in Portugal, in France, have the work with the Atomic Energy Agency of France, and also we have Alain Bécoulet, which is the reactor engineering head of ITER, being in the board, helping us essentially get all the lessons learned from ITER, the supply chain, the research, and use it for our own sake. So with that, I just want to tell you 4 things. Commercial fusion is coming, both in terms of supply chain, industry, but also in terms of reactor. We think that stellarators can bring energy to the grid, and that electricity will have the lowest cost among all of the fusion devices because of the steady state operation of reactors. And Renaissance Fusion will be making pre-fusion products, both liquid metals or superconductors, that we will sell to sustain the financing of the company. With that, I'll open the floor to questions. You can email me, and thank you for your attention.